So welcome to our last lab session of number 13 of Socket Programming in C Laboratory series. So this will be the overall quick final overview of all the topics that we have covered throughout the lab sessions. And today we will not be covering any technical parts like source codes, writing codes, but rather than that, we will be taking a look at theoretical parts of all the lab sessions. So let's get to work. So the first one was about the overall steps of socket creation before connection establishment. Um, that contained 5 steps. So on the left side we have the server part, if you remember, and on the right side we have the client. So the server would create the socket as the client part, and the server, unlike the client part, would bind, then listen, then accept, and read and write, which is just exchanging messages, and then it would close and the client would just connect. And on the lab 2, what we did was we also covered the parameters of socket creation, which was domain, type, and protocol. And on lab 3, we talked about the internet addresses and how they're represented. So the internet address was the IP address, which was formally defined as an internet protocol. An IP address is a numerical label assigned to each device in a computer network. Basically, if you're sitting at home and connected to a Wi-Fi, that Wi-Fi would have its own network, and your device would have its own numerical address that would represent that device inside that network. So that would be your internet address, or in other words, logical address, right? And then there would be like 2 different kinds of representing IP addresses, classful and classless. Um, and then there was the second part of the internet address, that was a port number. Port number was not the address of your computer inside the network. Rather than that, the port number was the address of your process that has created that specific socket. That will be the port number, and it will be used to deliver a packet to a specific process or program. And then um, the next thing was the TCP/IP stack, which was the internet stack, Internet Protocol Suite, or TCP over IP stack is called so because the TCP and Internet Protocol work in tandem to provide end users with reliable data transfer or communication. And it will be consisting of 5 layers. First of which would be the application layer, where we would be writing our computer networks apps. And then there would be the transport, where we have the TCP or UDP protocols that provide support to the application layer. Next, we would have the IP layer, best effort, and then that would provide the service to the TCP and UDP. So all the layers would provide the support to the upper layer, and then the data link layer was close to the physical one that would just help the packet reach from one hop to another. Physical would be the bits on the wire. All right. Um, and then the next thing was the difference between TCP and UDP, as TCP was referred to as connection-oriented socket, and UDP sockets were referred to as connection-less socket. TCP protocol would guarantee complete transmission of data, while UDP would. Um, and there would be the TCPs. I want to make one more note that TCP confirms each packet separately, and UDP does not. So that's the difference. Like UDP just sends without having to know if the packet was delivered or not, and TCP makes sure that each packet is delivered to the end computer. That was the biggest difference in a high level of abstraction. All right, the TCP server's iterative approach was created in the following order. After socket creation, binding, and listening steps, we would repeat the next steps, where we would accept a client, exchange data, read and write, and then close that socket, and then we would accept the next clients. Therefore, we would call it iterative approach. So iterating through each client at a time, and this would have a problem of not being able to support multiple clients at a time, if you remember. And this problem could be solved by creating threads, processes, or using IO multiplexing, and so on and so forth, that we have covered, and which I will also talk about a little bit later. So the iterative approach looks like this, and I want you to make sure that you remember this. And then the lab 4-5, meaning this content is inside both of the lab sessions. The difference of the TCP and UDP was there is no need to call in a technical perspective, in a perspective of socket programming. Um, in UDP, we don't need to call listen and accept like in TCP. So that was like the technical difference between programming difference between TCP and UDP. And then if we would take a look at the life cycle of the UDP socket creation and ending, it would start from socket creation on both ends, and the server would bind it, and then uh, it would just receive and send the data. It would just jump to receiving and sending instead of listening and accepting. And the client side would just move on just like the server side, just to sending and receiving, after which it would close the socket. And closing socket does not mean closing the connection, because we don't consider any type of connection, if you remember, inside UDP. So this would be the life cycle of UDP socket. And then there will be a characteristics of UDP where the concept of the thing that I just said, like the concept of connection inside TCP, disappears when we move to UDP. Therefore, it is considered to be connectionless. So that's the keyword that defines the UDP. It is connectionless, and TCP is with connection, considers connection. Um, so we just create a single socket on the server side and another socket on the client side, which can just receive and send the data. And then the next lab 6 will contain the TCP half close, where half close would provide the ability to close the connection from just one side, meaning one side will still keep on sending data, and the second side will just be listening, meaning the other end wants to finish the connection, but the first end doesn't want to. Like if we see this example, if you remember this, the first host says, hey, I'm done sending data to you, which means I don't want to send any more data, and then we would just make TCP half close right here. And then host 2 would say, okay, then just wait for me to terminate. Host 1 terminates outgoing connection but not ingoing, and then host 2 says, after sending some data, host 2, okay, I'm also done. And after this, the overall socket would be closed. That was the concept of TCP half close, and if you don't remember, I advise you to go back and take a look at the video and try to understand in details. It would be made possible by this function of shutdown that would terminate the output stream, keeping the input stream open. The next lab session would contain the process of manipulating socket characteristics. Like after creating a socket, you would be able to either see or change, for instance, the size of the buffers, outgoing buffers and ingoing buffers, and the flags like broadcast, keep alive, or any kind of like error. Are there like error flags, or um, these flags will be grouped by the socket level, if you remember, protocol level, where this would be the socket level, and this will be the IP level, and this would be the TCP level. And they will be grouped like this is a proper. These are the properties of the IP protocol level, where we have the TTL, time to live, multicast, and so on and so forth. And the TCP would have the keep alive mobility max segment size, where we have segment is only like devoted to TCP, if you remember. And the sockets would have on an application layer, we would have the send buffers and receive buffers. And reusing the addresses, if you remember, that we would have a problem when our process would stop receiving some packet abruptly, like the kernel would kill our process, we would have a problem with reuse address, and that would be able to, we would be able to set it with manipulating socket characteristics and solve the issue. We wouldn't be able to bind to that address anymore, and so that's why we would manipulate socket characteristics. All right. So these protocol level constants are used as arguments manipulating these socket level options. And lab 5, lab 8 was about creating processes. Here we're making a smooth transition to multi-processing server. Before it was just single process. Now we're moving on to fork. Fork is the function that helps you create child process, and when you make a fork function call, the whole complete content of your process would be copied inside an operating system, generating a different process, and then it would follow the instructions after the fork function call. And then we would have a problem with zombie processes because we have such concept as parent process and child process, where the parent process will have the responsibility of cleaning up the resources that its child processes take up inside an operating system. Meaning the parent process would have to just read the result that comes out of the child processes, and that would be meaning as a signal to an operating system to clean up the resources that it takes up. So the concept of zombie process is basically that a child process has finished its job, but the parent has not yet read the result that it is providing. So that was the concept of zombie process. And formally it was zombie process, a process that has completed its job but not yet cleaned up. And we would use signals, move on to signals to handle the problem of zombie processes. And let's take a look at how signals looked like. A software signal is just simply a software generated interrupt that is used by an operating system to inform the process, which will be our process or parent process, about a specific event. Like it can be about that child process has terminated. We can just set a signal, ask for an operating system to generate a software generated interrupt to inform us that our child process has terminated, right? So that was how these signals were used. Like there's hang up process, interrupt process, like control C. When you click the control and C inside your command line, the sig int would be delivered to your process, and there would be sig quit, sig kill, sig trap, abort, and so on and so forth, like sig alarm. And we would use signal registration to ask for an operating system to let us know if some event occurs. In order to receive signals from other process must register to a specific signal code. Alright, so multi-processing server example. So we can see that after fork we would have child processes, and after that we would have to close the client socket from the parent process and the parent the server socket from the child process, and it will be leading up to changing this visualization to this one, where we don't have the client socket on the parent process and child socket on the server socket on the child process. Meaning the parent process will be only responsible for accepting clients, and the child process will be responsible to exchanging messages with each separate client. And we would use signals to handle the zombie processes, and overall the multi-processing would work fine to solve the problem of iterative TCP server problem, where we wouldn't be able to support multiple clients at a time. So multiprocessing would be made possible in this fashion. All right. The next would be a little bit extended version of the multiprocessing, where we would be using IPC to make the parent process and child processes communicate with each other in cases like the one of the child processes would have to transfer the message to another child process, where the public chat that I have shown in the previous videos in the lab 9 would be possible, like the public chat where public chat, one client sends a message and one child process on the server side would receive it, and it would broadcast that message to all processes so that the message will be transferred to all clients at a time. And that was made possible by inter-process communication. And the formal definition of it is like inter-process communication is a mechanism which allows processes to communicate with each other, communicate with each other, and synchronize their actions. The communication between these processes can be seen as a method of cooperation. And IPC, like basically you can understand as a data transfer between two processes. And that data means a message in our case. The next would be without bothering with multiple processes, using just a single process to support multiple clients just at once. That would be made possible by I/O multiplexing, where we would use a single resource to support multiple ends, meaning we would be only uh, able to support multiple clients by neglecting small insignificant delays that we cause by making clients wait for each other in exchanging some messages, which would not be noticeable, like it would be in milliseconds. Like similarly, the transmission and reception of data is also possible for multiplexing because it does not have to be serviced with zero latency. And this is a very important point. It will not be zero latency, but it will still make still very small insignificant delay. And just by neglecting that, we would be able to support multiple clients at a time. And steps taken for I/O multiplexing were just divided into three, where first we would configure, second we would request change, third we would getting the change and confirming the responses, meaning that some sockets have changes in them. We would just read the change inside those sockets, meaning one client sends a message to us. We would notice it by first configuring that we want to change, listen to the changes on that socket, and then we would request the change, and then we would get the change after a client sends a message to the server, and then we would read the message, the connection request, or it can be just a message like a broadcast message or something. It would be just like the point is like I/O multiplexing would be divided into three parts: configuring target descriptors for observing their chains. The second step, requesting change in the observation. Three is getting and confirming the response. And then the next thing was Lab 11, one of the most recent ones, which is the use of threads, multi-threading TCP server and TCP client. Like the simplest way to understand would be to observe it on an operating system's level, where we would have multiple processes. So the operating system would be split into processes, and those processes would be split into threads. So meaning threads are the smallest possible units of execution inside the operating system, and that would lead to a less overhead for a CPU by means of a smaller context switching. The context of threads are much more lightweight than processes, and CPU doesn't have to do a lot of bunch of work to load all the values inside a process all the time to switch between the processes, and that would make the work of executing multiple like concurrent execution much easier. So multiple processes can be created within an operating system, and multiple threads can be created within a single process. And inside a worker thread model, by using threads, the main process would split the task into separate parts, like divide and conquer. It would divide into several parts, assign the task to separate threads, and those threads would finish their job. And by the time that those threads finish their job, the process would be just joining the thread, meaning the process would be just waiting for a thread to finish its job and waiting for another thread to finish its job as well, and then it would gather the result and print out the result. Like it could be downloading 1 GB of data, splitting up into several threads and downloading by parts, like 500 megabytes by one thread and 500 more megabytes by another thread. And then at the end, when it's 100%, just gathering the result inside the main process. That would be the worker thread model. In worker thread model, the threads will do all the heavy work and submit the results to the caller, to the process, and the caller gathers the result from the threads. Alright, there would be a problem when we would use multiple processes that would try to access the same global variable. We would have a problem of simultaneous accesses. For instance, if you try to remember, there would be just one global variable called num, and two threads will try to increment it at once, and the expected execution would be like if the initial value was 99, one thread would update the value, like retrieve the value 99, increment it and store the value of 100. The second thread would get the value of 100, update it and store it. We would have 101. So the two threads add one value at a time and increment the value from 99 to 101. That would be logical. So that's what we would expect from multiple threads to work like. But in reality, it wouldn't work like that because of the problem of simultaneous accesses. The problem um, can be explained like this. So we have the value 99, and if we make a note on one thing, that when you make a very small operation like updating a value by one, what the CPU is actually doing is it's retrieving the value, updating the value, and then storing the value back to that memory cell. So meaning the value will be stored from the memory area to the register, incrementing, storing back to the memory area. So there are three actions, and those three actions will not be synchronized between threads, and the value of 99 will be stored to both threads at once. So the first actions will be done like at once, and then the second thread will update the value. The first thread will not know that the value has been changed to 100, and it would store the 100 also as well, and we would have only +1. Instead we were expecting +2. Like from 99 we were expecting it to change to 101, but we see what we see in fact is 100. So that was the problem with simultaneous accesses, and that would be solved by critical sections. The critical section is the lines of code that will not be executed by multiple threads at a time. So it will be just called executed by a single thread at a time. So that's the critical section. Critical section is a set of instructions which should be executed on a single thread only. And that is made possible by such locks, like in example, it could be mutex, if you remember. If you don't, please take a look at lab 11. You will see the mutex. This second, one of the last slides, the lab sessions were about DNS. The DNS was a way to cover the numeric representation of address of computers with human readable text, so that we wouldn't have to memorize the computer's numbers, right? The IP address, which is the source of information for us. If you're just trying to get any information by opening up your browser, what you're trying to do is actually just retrieve some bytes from another computer. And if you want to do it, you actually have to know the address of that computer, just like if you try to get the package from someone. If it's not delivered, you would have to go and take it yourself, right? And you would have to know where to go. And that's the thing, like you have to know the address, and that address is inside computers. It's covered up by a textual human readable value like naver.com, and naver.com would be translated back to the computer address using the term of DNS, which stands for domain name system. All right. So to connect to a server, we need a machine-readable numerical address. DNS allows us to provide human-readable domain name instead of a numerical IP address. The client requests an IP address for the given host name, which is naver.com, and the DNS server would be responsible to provide the numerical IP address of the Naver's server to the requesting client. So that would be just overall rough explanation of DNS. And if you want to take a look at how the DNS works in details, please go back to the lab 12 and just watch the video, please. And I just gave you a rough understanding about DNS. And what we were actually considering, actually not considering, memorizing inside the DNS operations in a programming perspective, in a technical, very technical perspective, in a very technical language, was the structure of host entry that would have these five fields. The first would be the official name of the host. The second would be the aliases, which would be equally powerful, textual, human readable names of the server as the official name, and the address types and address length, which is just the IPv4 properties. The address list would be the machine readable dot separated IP addresses like 129.27.0.0.1. Those would be the result of DNS query and DNS response. The values inside the HAdder list field would be filled after DNS query. So that was the whole point of the Lab 12, like to show you that the text was converted to the IP address, numerical IP address by DNS queries, where we would not have to bother with DNS details because we didn't have to actually make DNS queries. Like we just said, we want to get the IP address for this naver.com, and then it would just provide it like automatically. And even though we didn't have to worry about it, we have to understand what we are actually seeing right here. And this slide was about that, to make you understand what you're dealing with, even though you don't have to deal with deep technical details of DNS. But you should know what is HNAME, you should know what is HAliases, and you should know what is HAddress list. And I believe now you understand what these are. If you don't, please don't hesitate to visit High Tech Building 1008 on Monday or Tuesday from 5 p.m. to 6 p.m. And before visiting, please make sure to send me an email and inform me. Thank you for paying attention, and I hope to see you on final exams.